So at the beginning of this screencast, let us just recall what we have done in the previous lecture, at least some parts of what we have done. So if you refer to the diagram given on the right hand side of the screen, there is a particle over here which is executing circular motion, and that particle's speed need not be constant with respect to time. It's not necessarily UCM. It could be going faster and faster or slower and slower. It's a general case we are considering. So the particle moves from position A to position B in a time delta t. R bar is the initial position vector, which in this case is also called the radius vector because the particle is moving along a circle. Now the other position vector, the new one over here, that's of course r bar plus delta r bar, where delta r bar is the change in the position vector. So obviously delta r bar is the displacement of the particle, the linear displacement. It's nothing but this vector AB bar, that's delta r bar. Theta is the angular position of the particle initially, and it is analogous to the coordinate of a particle moving along a straight line. Delta theta is the change in the angular position, which is called the angular displacement. D theta bar is an infinitesimal angular displacement which occurs, let's say, in an infinitesimal time interval, which could be called dt. Now, as the symbols indicate, delta theta is in general considered to be not a vector because it doesn't follow the parallelogram law of addition of vectors, although it has a magnitude and a direction given by the right hand rule. On the other hand, d theta can always be treated to be a vector because it fulfills all of the conditions necessary for that. In the particular case of two-dimensional motion, like in circular motion, delta theta could be treated to be a vector because delta theta obeys the parallelogram law of vector addition as long as the motion of the particle or of the object is restricted to two dimensions. Omega bar is the symbol for the angular velocity of the particle, and its definition is d theta bar by dt. It has the same direction as d theta bar, which is given by the right hand rule. For example, in the diagram, if the particle moves from A to B, then the right hand rule tells us that d theta bar, I'm assuming that this is an infinitesimally small angular displacement, so you can call it d theta. So the right hand rule tells us that d theta bar is out of the plane of your screen, and so would omega bar, because you are essentially dividing d theta bar by a positive number dt. So that's how to find the direction of omega bar by the right hand rule. Alpha bar is the angular acceleration, and it's defined as d omega bar by dt, and like omega bar, alpha bar is also in this figure either out of the screen or into the screen. So the rule is, if the particle is speeding up, it means alpha bar is helping the omega bar vector to grow, and that would mean that alpha bar is in the same direction as omega bar. This corresponds to the particle speeding up. On the other hand, if the particle is currently slowing down, then alpha bar doesn't help omega bar to grow. On the contrary, it decreases the length of the omega bar arrow, so alpha bar is in the opposite direction as omega bar. Now what we want to do next is to attempt to find a relationship between the linear velocity of the particle, which is of course defined by dr bar by dt. So dr bar would be ab bar, the straight vector. Assuming that it's very small, this displacement happens in a infinitesimally small time, so the displacement would no longer be delta r bar but dr bar. So on the one hand, we have the linear velocity of the particle, and we want to relate that with the angular velocity, which is omega bar, which we have defined as d theta bar by dt. Now omega bar is the rate at which this particular radius vector is going round and round like that, and its unit is of course radians per second, whereas v bar is the well known linear velocity and its unit is meter per second. Now we have seen in class that v bar and omega bar do not bear a simple relationship to each other. So for example, if mod of omega bar let's say is the same for two particles, then mod of v bar need not be the same. It depends on the radius of the circle. So if you are whirling a stick like this around this point, this end point of the stick, so the stick is going in a circle, and if I consider 2 points, I'll call them P and Q. Now both of them execute their own circles, and both of them execute a circle in the same time interval. Obviously, it's the time interval required for the stick to complete a full rotation. Now assuming that the value of omega is constant, it would mean that both of these particles had uniform circular motion with the same omega. That doesn't mean that their linear velocities, that is Vp bar and Vq bar, it doesn't mean that these have the same magnitude. In fact, the point Q, it travels faster than point P, and the reason is, in the same time it has to cover a greater distance. The circumference of its circle is larger than the circumference of this circle, so naturally one can conclude that point Q travels faster. So its linear speed is larger than the linear speed of P, in spite of the fact that the omegas are the same. So in short, the V bar omega bar relationship is not straightforward. It is complicated by the fact that the radius of the circle along which the circular motion takes place is also going to get involved in the V bar omega bar relation. So that's precisely what we want to do now. We want to derive a relationship between the linear velocity, that is V bar, and the angular velocity omega bar of a particle which executes circular motion. Now to do that, we refer to this figure on the right hand side, and what we are going to do is to pretend that this delta theta is actually d theta. It's an infinitesimal angular displacement. It's not actually. The figure necessitates that this angle be shown as a large angle, otherwise the figure itself doesn't become very clear. But you just use your imagination, assume that d theta is infinitesimal, in which case delta r bar will have to be written as dr bar. So delta r bar is of course the vector which begins from A and ends at B, and that's dr bar now. And because this dr bar is so small, it means that the length of this arrow, that is modulus of dr bar, is going to match the length measured along the circular arc AB, and that's because there is very little difference between the straight line path from A to B and the circular arc from A to B, and that's because this angle d theta is so small that B and A are almost adjacent points. The figure of course exaggerates all this, but if B is more or less the adjacent point of A, then it makes no difference. You can't distinguish between a circular arc and a straight line segment. That's why I'll just repeat, the length of AB bar, the straight vector, is going to be equal to the length of the circular arc AB because of the infinitesimal displacement involved. So the first thing that we do is to write the well-known geometrical relation, that is S is equal to r theta. We apply this relation in the context of the particle's motion from A to B. So it means the length of arc AB. Now the length of arc AB, as explained just now, is actually the modulus of the straight line segment AB. So it's mod of dr bar, and that's equal to the radius, which is mod of r bar, multiplied by the angle, which is mod of d theta bar. So that's S is equal to r theta, written in terms of this particular displacement from A to B. Now this is an exact relation, and the relation is not going to be spoiled by multiplying the right hand side by 1. Now why am I going to do it? It will be clear in a moment. I am going to multiply it by 1, which is actually sine of 90 degrees. And the reason I am doing it is that these three quantities are vectors, and not only are they vectors, they are mutually perpendicular. I'll just explain this. I'm trying to make this look like a cross product, or the magnitude of a cross product, but let's see why they are mutually perpendicular, these three vectors. So dr bar is the vector AB bar. I'll just show the direction of dr bar over here. Dr bar is like that. Now r bar, on the other hand, is perpendicular to dr bar. This angle over here is actually going to be 90 degrees in the limiting case when B is very close to A. It doesn't appear to be 90 degrees in the given figure because the figure is an exaggerated version of the actual case. So this angle over here is 90 degrees. In fact, what I can do is I can shift this dr bar, or rather r bar, over here. So it is this angle which is 90 degrees. And finally, if you look at d theta and try to find its direction, or the direction of d theta bar, that is, you have to apply the right hand rule. So apply the right hand rule to d theta bar, and you get a vector which is coming out of the screen, the plane of the computer screen. So I'll write it over here. That represents d theta bar. As you can see, these three vectors r bar, dr bar and d theta bar, which are involved in this multiplication, are mutually perpendicular. And incidentally, the angle between r bar and d theta bar, if you look at this figure, the angle is 90 degrees. So it means that you've got these vectors where these two have an angle of 90 degrees between them, and on the right hand side you're multiplying two vectors, their magnitudes, with the sign of the angle between them, and as the answer you get the magnitude of a third vector, where the third vector is perpendicular to this as well as perpendicular to this. So I'm sure that this reminds you of the vector product or the cross product, that particular operation which we did in vectors. So you can of course expect this relation to be actually nothing but the magnitude. The right hand side is nothing but the magnitude of a cross product. So it's going to be dr bar, it could be equal to r bar cross d theta bar, or we're not sure, there are two possibilities. Dr bar could also be d theta bar cross r bar. It's one of these two. Let's look at it again. If it were this, and you know that the angle between r bar and d theta bar is 90 degrees, then the mod of dr bar would be the mod of this into the mod of this into sine of 90 degrees. And if this were the correct relation, and you know that this angle is 90 degrees, you do the same thing. Mod of dr bar is mod of d theta bar into mod of r bar into sine of 90 degrees. So it's either this or that. It's not sure at this stage, and that's exactly what we want to find out. So the magnitude of dr bar you get correct, even if you whatever relation you assume, the first one or the second one, the magnitude is not going to be problematic. It's the direction which is going to be problematic. So with one of them you are going to get the correct direction for dr bar, and that will be the equation that we, or the formula that we eventually choose. So going back to the figure on the right hand side, you just do apply the right hand rule to r bar cross d theta bar first. That's the first relation, and when you do that r bar cross d theta bar, I'm sure that you'll get a vector in this direction. It's not dr bar, in fact it's in the opposite direction of dr bar. So the first relation doesn't seem to work, it seems to be wrong. And on the other hand, if I write the second relation, that is dr bar is d theta bar cross r bar, if you do this d theta bar cross r bar, then you actually get a vector which has the same direction as dr bar. So it is this equation or this formula which is the correct formula, and this is obviously wrong. So we accept this formula. Dr bar is d theta bar cross r bar. Dr bar is the displacement from A to B, the straight line displacement. D theta bar is the corresponding angular displacement. R bar is the original position vector drawn from the origin O to A. Now if I divide both sides by dt, the small time interval in which this displacement happens, I get dr bar upon dt on the left hand side. Now that's nice. We want this, we want it to be the velocity, so you got the velocity equals. Now you can choose to put dt below this term or below this term, it's up to you, but I'll put it below d theta bar. So what I get is d theta bar divided by dt cross. Remember, it's a cross product, so there are two vectors involved on the right hand side, so you have to maintain the proper symbol, d theta by dt cross r bar, and you have to maintain the proper sequence also because it's a cross product. Now d theta by dt is nothing but omega bar, namely the angular velocity. So my relation finally becomes v bar, that is the linear velocity of the particle, is equal to the cross product of number 1 its angular velocity and number 2 its radius or its position vector, and that's one relationship which you should remember, the velocity in terms of the angular velocity. Now this relation is usually remembered, as far as problems are concerned, in the scalar form. So while converting a vector to a scalar relation, you must remember to allot positive conventional directions. So anything which is consistent with the direction of motion, which is anticlockwise, you take it as a positive scalar. So let's look at v bar. So for the positive direction, or the conventional positive direction for v bar, would obviously be along the tangent at A and in that direction, because that gives rise to an anticlockwise motion. So that's the reference direction for v bar. And once you begin to write this as a scalar relation, then on the left hand side you write v. So v is the scalar component of the velocity in the direction of this blue arrow, and that's equal to, now omega bar, you're going to again treat that direction of omega bar as positive, as the conventional positive, which is consistent with the motion of the particle in the anticlockwise direction. So if the motion is anticlockwise, will mean omega is out of the plane of the screen. So that's the conventional direction for omega bar, and if you adopt that conventional direction, or in other words, sometimes you can say in place of this, sometimes people say anticlockwise direction. A vector omega bar, like omega bar, which technically has a direction like that coming out of the computer screen, that direction comes because the direction of motion of the particle was anticlockwise. So technically speaking, one should say that the direction of omega bar is this, but sometimes we'll be saying that the direction of omega bar is this. It means the same thing, although technically you are a bit wrong in saying this, but it makes a lot of sense because it gives you the direction of motion, the anticlockwise direction of motion. So it leads to a better perception or visualization of the problem. So anyway, we are not going to do this right now. We are going to say omega bar comes by convention. The conventional direction of omega bar is out of the plane of the computer screen in this particular diagram. And then in that case, I just write the right hand side as omega times, now mod of r bar is simply the modulus of the radius. There is no sign involved there, so I just write this. Usually it is remembered, for better or for worse, as v is equal to r omega. I think that's more, it has a rhyme to it. Maybe I don't know why, but people usually say v is equal to r omega, and the problem is, once you remember v is equal to r omega, then writing this is going to be a bit difficult. You will tend to write v bar is equal to r bar cross omega bar, whereas the reverse is correct. So you can memorize it any way you want, but be careful in writing the vector relationship. If needed, you write it properly. So v equals r omega, and if you want, sometimes people write this in the form of a vector relation in a slightly different way. This relation is sometimes written as v bar equals r omega times the tangential unit vector. So you have to assume that there is a unit vector in the forward direction, meaning in the direction of motion, and that you call u t for tangential cap. So all you do is you take this r omega and then you multiply it by, well, that's a scalar r omega, and you multiply it by ut cap to convert it into a vector. It is essentially the same relation, no different. It's a vector relation which gives you the value of v bar. Now we can just spend a few moments investigating and getting comfortable with the relationship that we have just derived. So this diagram depicts a particle which is moving in a circle in the anticlockwise direction, and let's say that the angular velocity is omega. So basically, if I draw this radius vector, then this radius vector is going round the origin like that and like that at a rate of omega, which is measured in radians per second. And further, let's say that the linear speed of the particle, which of course is going to be tangent to the circle, that linear speed is v, or better still, we can say the component of the velocity, the scalar component in the forward direction, is v. So omega is the rate at which this vector goes round, and v is the scalar velocity in the forward direction. Now obviously if omega grows, if omega becomes large, then v is going to become larger. So there is some sort of relation between omega and v, but that's not all. It's not such a simple relation. It also depends on the radius of the circle. So the relationship is this linear velocity in the forward direction is given by the radius of the circular path times omega. And a nice way to illustrate the physical significance of this relation is to set up a small thought experiment in which you have a rod, let's say, which is rotating about a pivot at the end point. So AB is the rod, and the rod is itself going like that, rotating about point A. So after some time, for example, the rod will be like that. Now just imagine that this angle is changing at the rate of omega, and omega is constant. Let's assume that. So imagine that there are two particles, dust particles, which are on the surface of the rod. One of them is over here, I'll call it P, and the other one is over here at the end, I'll call it Q. Now both of these particles, they are moving in circular paths, they have circular motion. In fact, since omega is constant, and you know that these particles move at the same omega as the rod, so constant omega would mean UCM. So these particles are essentially going to travel with UCM around point A, and the angular velocity is omega for each of them, because both of them are attached to the rod. So if you're not convinced, you can just imagine that one of the particles, the particle P, has a radius vector like that, and the second one has a radius vector like that. So the blue vector and the red vector which I've drawn, both of them are going to sweep out equal angles in equal time intervals. So they are always going to coincide, or at least overlap. Now is there some relation which you can see by common sense between Vp, the linear velocity of P in the forward direction, scalar velocity that is, and Vq? So let's try a common sense approach first, and then let's try to derive the relation using the formula which we have just derived, namely V is equal to R omega. Now common sense says that particle P is going to go round like this. It's going to cover a distance equal to the circumference of that circle, and therefore Vp is going to be the circumference divided by the time required to cover that circumference. I'm not sure whether I said that, but I'm going to assume that this distance, the radius of that circle, that is the distance of P from point A, let's say it's half of the length of the rod. So the circle which is executed by P has a radius of L by 2, and since point Q, or dust particle Q, is at the other end of the rod, the radius of the circle executed by Q is going to be the length of the rod. So that is double of the other radius. Now what we get here is Vp, the scalar velocity of P in the forward direction, is the circumference 2 pi into L by 2, that's the radius of the circle executed, divided by the time required to complete one circle. On the other hand, the scalar velocity of Q is the circumference of its circle, but remember it's a bigger circle now, so the circumference is 2 pi into L. L is the radius of the bigger circle, and both of these particles P and Q, they complete a circle in exactly the same time, so t. Now compare these two, and immediately you see that Vq is double of Vp. That's a common sense approach. Now, do you get the same relation when you apply V is equal to R omega? Let's see. The velocity of P is R times omega. Now remember, the circle which P executes has a radius of L by 2. So L by 2 multiplied by omega. And the velocity of Q is R omega again, but this time the radius of the circle is L, and omega is the same as that omega, so omega. Now dividing the second equation by the first equation, you get Vq upon Vp is equal to 2, and that's exactly this relationship which we derived by common sense. So I hope that this particular example gives you a feel for the formula V is equal to R omega. Remember that the scalar velocity not only depends on how fast the radius vector is going around, that is, depends upon omega, but it also depends on the size or the length of the radius vector r. So we can now proceed, once we have derived the relationship between the velocities. I hope you understand what I'm saying. Which velocities? We got the relation V bar is equal to omega bar cross r bar. That was the vector form. Now this is the linear velocity. So on the one hand we have got the linear velocity, and on the right hand side we have got the angular velocity. So it's a relationship between the linear and the angular velocities. That's what we have just derived. We can now go ahead and try to derive a relationship for the acceleration of a particle in circular motion. So to understand the formula for the acceleration, to derive it, we again look at the same picture where you have this particle executing circular motion of radius r, and the instantaneous linear velocity of the particle is v bar. The instantaneous angular velocity is omega bar, which is of course d theta bar by dt. Theta is the angular position, and alpha bar, which we have said earlier is the angular acceleration of the particle. We have also defined it earlier to be d omega bar by dt, and we said that alpha bar and omega bar both are vectors and both have directions, of course. So if you look at the diagram, then you have to imagine the z-axis which comes out of the plane of the screen. So omega bar and alpha bar would be along the z-axis, parallel to the z-axis, either with the z-axis or against the direction of the z-axis, but both of them would be parallel to the z-axis. And in particular, if you have a scenario where the particle's speed is increasing with time, then alpha bar would be in the same direction as omega bar. So in this case, of course, the right hand rule says that omega bar is coming out of the plane of the screen, that's along the positive z direction, and so would alpha bar if the particle is speeding up, and if the particle is slowing down, then alpha bar and omega bar would be in opposite directions. So that's the sort of theory that we did a bit earlier, and now we can proceed and try to find the acceleration of the particle. Remember, we are talking about a general case of circular motion, not necessarily uniform circular motion. So this particle is going round and round, and it may be going faster and faster or slower and slower. So it's a general case, as I said. Of course it may be in UCM because that's a special case, but you can't assume that in the beginning. Now we said earlier, not in the screencast but probably in the earlier lecture, we said that this particle in general will have two accelerations, well, two acceleration components, let me put it that way, and one component is the normal component of the acceleration, and that points towards the center of the circle in this case, and we call it a normal. It's surely an is a positive number, surely, because we are sure of the direction of an bar. It's inward, radially inward. So if you want, you could call it an bar because you're sure of the direction. And the second component of the acceleration is going to be tangential. So it's called a suffix t. And here I don't put the bar sign on top because I'm not sure whether it's actually in the direction of motion or opposite to it. If it's in the direction of motion, that signifies a particle which is speeding up. Otherwise, in the opposite direction would mean a particle which is slowing down. And if it's 0, of course, it means a particle in UCM. So I don't put a bar sign on top of AT like that because I want to allow AT or AT bar to be in the opposite direction, which will happen when AT is negative. You're not sure of the sign. So it's a very general thing you're doing. And now what you do is to derive a relationship, a formula which gives you the total acceleration. Now in this case, for example, the acceleration we are talking about would be the vector sum of these two. Assuming that AT is positive, then this rectangle which I have drawn is correct, and the total acceleration would be in that direction. Of course, if AT is negative, then the rectangle would be in this region and the resultant acceleration would be this. So that's the total acceleration. The idea is I want to find a formula which tells me the total vector acceleration of the particle, and you know this to be dv bar by dt. That's a very general formula. I'll just write it over here. The acceleration of the particle is the rate of change of the instantaneous velocity of the particle. Now what you do is to use the formula you have derived earlier for the velocity. So it's going to be d of omega bar cross r bar by dt. That's the formula for the instantaneous acceleration. You know, the sort of acceleration that is depicted by this arrow, for example, if AT is positive. So the total acceleration is given by this. And now we use our rules of derivatives, and I must have discussed this in class, where omega bar cross r bar is itself a function of time, and this new function of time, you want to find how fast it changes with respect to time. That's the meaning of this derivative. So you must maintain the sequence of the terms when you expand this derivative. So anything involving omega will come first, anything involving r bar will come second. So it's going to be omega bar cross d r bar by dt, that's the first term, plus, now you find the derivative of the first term and remember to place it first. Omega terms must come first. So d omega bar by dt cross r bar. That's the first step. You just use the formula for the derivative of a product function. So the acceleration turns out to be, I'll do some simplification now. Omega bar is the same, but dr bar by dt is essentially the linear velocity of the particle. Dr bar by dt is the rate of change of the position vector with respect to time. This is something that we have done in kinematics of particles in the very beginning, plus d omega bar by dt is alpha bar, is the angular acceleration. So I just write that alpha bar cross r bar, and that's a formula that you have got for the total acceleration of this particle. Now we are interested in actually isolating these two components, these two mutually perpendicular components, and we seem to have got one formula for the acceleration. And I will now show to you that these two terms, this term and this term, each of these terms actually corresponds to one acceleration component, either the radial component, the normal component, or the tangential component. It's such a nice and convenient formula. It directly gives you the two acceleration components which you are interested in. So how does that happen? To show that these two components are actually the normal and the tangential components of the acceleration, we just find what is the direction of omega bar cross v bar and alpha bar cross r bar. So let's look at this one first. In the picture, you see that the particle is moving in the anticlockwise direction like that, and therefore if you apply the right hand rule, then omega bar is actually coming out of the computer screen, and v bar is in the forward tangential direction, so it's like this, in this direction. So this vector is omega bar and this vector is v bar, and if you actually apply the right hand rule to find the direction of omega bar cross v bar, then you'll get a direction like that. Omega bar cross v bar would be in that direction, and you can see that that direction actually corresponds to the direction of the normal acceleration, this direction, centripetal, center seeking. So we may suspect that this component is actually the centripetal acceleration, but it's still not perfectly clear unless we can prove that this is the tangential acceleration. So we'll try to do that. Now let's look at the direction of alpha bar cross r bar. Alpha bar cross r bar is not all that straightforward, because there are two possibilities. So possibility number one is that the particle is speeding up, in which case alpha bar will be in the same direction as omega bar. So when I do this alpha bar cross r bar in that case for possibility 1, then alpha bar is, since it's in the same direction as omega bar, alpha bar should be like that. Okay, and r bar is in this direction. So what I'll do is I'll just shift the vectors. So this is alpha bar, and r bar is in the radially outward direction. Now when you do this alpha bar cross r bar, what you get is a vector in this direction. That's alpha bar cross r bar, this blue vector which I've drawn, and it's the second component of the acceleration. And if you go back to the picture on the right hand side, you see that alpha bar cross r bar in this case is in the forward tangential direction, just as omega bar cross v bar was in the radially inward direction. Now this direction of alpha bar cross r bar is consistent, it is identical with the expected direction of at bar, because we just said that in this particular possibility we are assuming that the particle is speeding up. So naturally the tangential acceleration must be in the forward tangential direction. The tangential acceleration must be in the forward direction because the particle is speeding up. On the other hand, if we consider the possibility, the second possibility, that alpha bar is in the opposite direction of omega bar, so it basically means that the particle is slowing down. Now in that case, what happens is alpha bar is that vector in that direction into the computer screen, r bar is of course still radially outwards, and you get a vector alpha bar cross r bar in that direction. Now if you just draw it in the right hand side diagram, you get alpha bar cross r bar, alpha bar cross r bar to be in the backward tangential direction, and that is the expected direction of a tangential bar under the given case where we are assuming that the particle is slowing down, and so the tangential acceleration must be in the backward direction. So it's clear that this must correspond to a tangential bar, and on the other hand this must correspond to a normal bar, or the the centripetal acceleration, a normal bar. So just to summarize everything, in circular motion the acceleration of the particle can be expressed as the sum of two rectangular components, a normal bar, and this is the component which actually changes the direction of motion of the particle, and the second rectangular component is a tangential bar, and this is the component which changes the speed of the motion, that is the modulus of the velocity, or more properly it changes the scalar velocity v. So you have two different components doing two different jobs, and we've got a nice formula now for the normal acceleration as well as the tangential acceleration. So the normal acceleration, or the centripetal acceleration, is actually equal to omega bar cross v bar, and the tangential acceleration, whether it's in the forward or in the backward direction, it's always going to be equal to alpha bar cross r bar. And there's another way to express this. So what we do is we recognize that, look at the first component, omega bar cross v bar. So omega bar and v bar are mutually perpendicular, and therefore the magnitude of this component is going to be omega into v into sine 90 degrees, or what you get is essentially omega into v is the magnitude of the normal acceleration, and then you just have to multiply it by a unit vector in the normal direction, that is in the radially inwards direction, plus, now before I go to the second term, just something about this omega and v. Omega and v, you could say that they are the absolute values or the magnitudes of omega bar and v bar. That's what happens in the magnitude of the cross product. The magnitude of the cross product is mod of omega bar times mod of v bar, and then I multiply it by u n cap, so that I get back a vector. Now that's one way of looking at omega and v. Now the second way to look at them is that omega and v are the scalar, angular and linear velocities, and once I try to convert a vector into a scalar, I have to allot certain reference directions to the vectors involved, and these reference directions I take care that they are mutually consistent. So what do I mean by that? I'll just tell you again what I'm trying to do. I'm trying to view these omega and v things as scalar components. You could view them as magnitudes, but you can also view them as scalar components, provided that scalar components, or rather I would say you could view them as scalar velocities, be it angular or linear. Now you could do that provided that you are consistent in the allotment of directions. So for example, in this given picture, the particle is going around like that, correct, in the anticlockwise direction. So if the particle goes in the anticlockwise direction, then the conventional direction, well, it would mean that omega is actually in this direction, right, coming out of the plane of the computer screen. So what you do is you allot this direction as the positive direction. You allot this direction as positive for omega because it is consistent with the direction of motion of the particle, which is actually in the anticlockwise direction. So in short, if you want to find the reference direction for omega bar, so that you want to you can convert it into a scalar, the easiest approach is to visualize how the particle is moving. In this case, it's moving in the anti-clockwise direction. Of course, if it's not given, then you can assume it doesn't really matter. So in this case, the particle is moving in the anti-clockwise direction, and then corresponding to that, the positive direction for omega bar must be out of the screen of the computer. So that's the positive direction for omega bar. And now we need to allot a positive direction for V bar. So remember, you have to be consistent. Once you say that omega bar is positive in this particular direction, so you just go back to the picture where you said that the particle is moving in this direction. That's why we got this direction for omega bar. And if the particle is indeed moving in the anticlockwise direction, then obviously the direction of velocity must be like that, according to the arrow which I just drew in position A. So the black arrow, this one which I drew, is the positive direction for V bar. That's the positive direction for V bar. So it's important that this arrow and this arrow, their directions are consistent with each other. So now you know that omega is positive in this direction in the given situation, because actually omega is, or omega bar is, in that direction. And you also know that V bar is positive, or V is positive if I assume this conventional direction, because the velocity is actually in this direction. So what it means essentially is that if you choose omega and V to be scalar, angular and linear velocities in this direction and in this direction respectively, then you got a positive number over here, and it's multiplied by another positive number over here, and this turns out to be eventually mod of omega bar into mod of V bar itself. So that's what I was trying to say. You can view them as the scalar angular velocity and scalar linear velocity, as long as they have consistent reference directions. And that's one way of doing it. And the second way is to assume that omega and V are mod of omega bar and mod of V bar respectively. The scalar velocity approach has certain advantages over the magnitude approach, and that will be clear when we look at the second component, which is alpha bar cross r bar. So let me try to write alpha bar cross r bar in the same way. So recognize first of all that alpha bar and r bar are mutually perpendicular vectors, and therefore their the magnitude of alpha bar cross r bar is going to be mod of alpha bar times mod of r bar into sine of 90 degrees, which is 1. So one way of doing it is mod of alpha bar into mod of r bar into sine of 90 degrees, and you have to now multiply it by a unit vector in the tangential direction. And here you run into a problem, because sometimes this the tangential acceleration is in the forward direction, that's when the particle is speeding up, and sometimes it's in the backward direction, that's when the particle is slowing down. And so you have an ambiguity in the formula over here. So for example, if you say ut bar is the unit vector in the forward direction, that is in the direction of motion, then you have to insert a plus or minus sign over here, because you are not sure whether the particle is speeding up or slowing down. The plus sign is applicable when the particle speeds up or is speeding up, and otherwise when the particle is slowing down, it's the negative sign, and you usually don't want a formula having a plus or minus sign like that. So there is a way out, of course, and the way out is to not take the mod of alpha bar and mod of r bar, but rather you deal with the scalar components, and then you depend on the sign of alpha into r to give you the proper sign, so that you don't have to actually insert a plus or minus sign over here, and I'll show you how that works. So I'll just rub this out. I don't want it that way. Now I first of all write r. Okay, r is simply the radius of the circle, so there's no scalar component involved. R, you can treat it as simply mod of r bar. That's okay, that's not an issue. The sign is going to come from alpha and not from r. So r signifies the radius, which is mod of r bar. Now let's go to the important component, alpha bar. So I'll write alpha. Now alpha is not the modulus of alpha bar, but it's the scalar component. It's the scalar angular acceleration. It's alpha bar expressed as a scalar, and as you remember, whenever you express a vector as a scalar, you have to allot a certain positive direction. So the rule is, if you have allotted a positive direction for omega bar, we have done that over here. This is consistent with the direction of motion, which is in the anticlockwise direction. So you be consistent, you allot the same direction for alpha bar as positive. So both alpha bar and omega bar are they have the same common positive reference direction. It's a bit like in UALM. If you treat rightward as positive if a particle is traveling along a horizontal line, and if you treat rightward as positive, the convention is that U as well as V as well as A as well as S are all they all have the same rightward positive convention. You don't change the convention from one vector to the other vector. So you say that the direction of motion gives you the direction, the positive direction for omega bar, and you allot that same direction as the reference direction for alpha bar. Now what does this mean? This means that if the particle is speeding up, then since omega bar and alpha bar are actually in the same direction, okay, it would mean that alpha is positive. You see, in this case, let's go to this example. You know that omega is positive because it corresponds to motion in the anticlockwise direction, which means that omega bar is actually coming out of the plane of the screen, which means that omega is positive. Now since the particle is assumed in this case to be speeding up, and we'll do the second case just 1 minute afterwards, if the particle is speeding up, then alpha bar also comes out of the plane of the screen. So that means that both omega and alpha have the same sign. Both of them are positive. So under this sign convention, if the particle is speeding up, then alpha is positive. R is anyway positive. You just have to multiply this with the unit vector in the forward tangential direction. So you get a positive number multiplied by a unit vector ut cap in the forward direction of motion, and that's exactly what we want, because now this arrow is actually the direction of at bar. It corresponds to a particle speeding up. So we are right if the particle is speeding up in saying that you just have to write this term as r times alpha. Now if the particle is slowing down, then omega bar and alpha bar have opposite directions, which will mean opposite signs. Omega is greater than 0 obviously, so alpha will be negative, and that would allot a negative sign to this product. You still multiply by the same old unit vector ut cap, which is in the direction of motion, the forward tangential direction, and you get an acceleration component which is in this direction, in the backward direction, as expected if the particle is slowing down. Particle is slowing down, remember, because we said that omega bar and alpha bar have opposite directions. So all in all, it seems that if I adopt this convention, this sign convention I just described, then this overall this equation is nothing but another form of this equation, and it gives you the normal and the tangential components of the acceleration correctly. So that's an alternative form of this equation in the box, and you can see that I've just put that new form in a box 2. So the total acceleration of a particle in circular motion is omega v un cap plus r alpha ut cap, where omega and v and alpha are all scalar. They are vectors which have been converted into scalars by the method which I just showed you. R is of course the radius of the circle, and this first component is the centripetal acceleration, where un cap of course is the radially inward unit vector. Now the second component is the tangential acceleration, where ut cap is the tangential unit vector in the forward direction, that is in the direction of motion. Now I'll just put it side by side with the other formula for the velocity. So the velocity is equal to r times omega, that's in scalar form, or the velocity in vector form can be written as r omega multiplied by u tangential cap, where omega is the, well, r is the modulus of the radius vector, it's nothing but the radius of the circle, and omega is the scalar angular velocity. So that's my other formula. So you know, if you use the scalar version of that formula, v is equal to r omega, you're going to get some alternative variations of this. So omega times v is also equal to, omega is v by r, so v by r into v, so that's v square divided by r. So one alternative form of this expression is, in place of omega v as the normal acceleration, you write v square upon r, and of course everything else is the same, un cap plus r alpha times ut cap. That's one form. And the second form, or the third form rather, is when you replace v with r omega over here. So what you get is omega times v is omega times r omega, so that actually gives you r times omega square. So my third form is r omega square times normal unit vector cap plus r alpha times u tangential cap. So there are three versions of this formula, and they differ from each other. Well, they are similar to each other in this, in the second term. So the tangential acceleration is always r alpha, r alpha, r alpha, but they differ in the first term. The radial or centripetal acceleration is given by three different formulae. One of them is omega into v, the second one is v square upon r, and the third is r times omega square. So you use any one of these three formulae, you will get the same answer. You use the formula obviously which is suitable to that particular problem, depending on the what data you have available. And another variation of this which you get in some books is the vector un cap. Now un cap we have taken to be a vector which points towards the center of the circle, like that. So sometimes what happens is you take a vector which points in the radially outward direction, a unit vector. Okay, un cap was also a unit vector, but if you take a a radially outwards unit vector, and let's say that you give it a name like UR cap. So it's clear that UN cap and UR cap have the same magnitude 1, but they have opposite directions, so they are negatives of each other. So this formula would actually look like this. You multiply by minus UR cap instead of UN cap, omega V. So A bar is equal to omega V into minus UR cap plus the same thing. So whether to write UN cap or minus UR cap, it's up to you. I would prefer UN cap because you don't have to write the minus sign, but if you ever see this in any book, etc., then please understand what they are saying. So to summarize this in a nutshell, if there is a particle which is moving, let's say, in this direction, in the anticlockwise direction along this circle, let this be the x-axis and that's the y-axis, then if you want to write the accelerations of this particle, there's going to be an acceleration in this direction which is equal to v square divided by r. Well, there are three formulae. The other formula is r times omega square, and the third formula is v times omega. So all of these give the same result, and you note that all these three are positive numbers. R omega square is obviously positive, v square upon r is obviously positive, and we know that they have to be positive because we are sure that the direction is radially inwards, and v into omega is positive because v and omega are both chosen consistent with each other, the reference direction. So omega is positive will always mean v is positive. So that's the normal acceleration, or it's also called the centripetal acceleration. And the tangential acceleration is, it is called a tangential, and the formula for that is r times alpha. Now r is the radius of the circle, that's positive, and alpha itself can be either positive or negative depending on whether it helps omega or it opposes omega. And a positive value of alpha would mean at is positive and the tangential acceleration is actually in the forward direction as shown in the diagram. A negative value of alpha would mean that the tangential acceleration is in the backward direction, and that's all consistent, nothing wrong in that. So this is the diagram in a nutshell, and that's the diagram for the accelerations. Now if in the same diagram I can draw the diagram for the forces, so I'll draw them in a different color. So this would be, the force component in that direction would be the mass times the normal acceleration. So the normal, that's called the centripetal force, by the way. So the centripetal force or the normal force is going to be mv square upon r, and it's towards the center. It could also be expressed as mr omega square or mv omega. You have to remember all the three forms. And the tangential acceleration, or rather the tangential force, is got by multiplying the mass. So F tangential is mass times r times alpha. Okay, this is actually a right angle, it doesn't look like that, but assume it is. And m or alpha, the tangential force, is either in the forward direction if the particle is speeding up, or it is in the backward direction if the particle is slowing down. So that depends on the sign of alpha. Now if you are wondering how to memorize this, well, it is a bit difficult to memorize in the beginning, but if you use these formulae in a number of problems, it will become all that easier. And there are certain similarities and things which you can look at, you can see, observe them. So for example, when you say V is equal to R omega, you notice that this V is a linear quantity, linear velocity, whereas this is angular. So it seems that when you multiply the angular velocity with the radius, you get the linear velocity. Now that same thing is valid for accelerations. Well, that's not strictly speaking true. It's valid for this component of the acceleration, the tangential component. It's not valid for this, but that might help you to memorize. So the tangential component of the acceleration, which is the linear quantity, but only one of the linear quantities, the one along the tangent, and that's given by the corresponding angular quantity, the angular acceleration multiplied by the radius. So this formula and this formula have some similarity, but the only difficulty is if you forget that there is another component of acceleration, this one. So don't do that, don't forget that. So what I have done is up till and including point 5 of the handout, or rather we haven't done point 5 completely. In point 5 there is something called special cases, uniform circular motion, and so on. So special cases onwards, we do it actually in the next lecture. So please take notes in this, understand whatever I have said in this screencast, take detailed notes, and we'll continue in the next lecture. Thank you.